SwayamPrabha. Digital India. Educated India.
Good afternoon, everyone. In today's lecture, we will cover explicit and implicit formulations, and we will discuss on stability. So, again, let us consider the model equation that we are using for explaining different aspects of finite difference quotients and formulation. This is unsteady state heat conduction equation, where U is basically temperature, T is time, alpha is thermal diffusivity, and X is the spatial dimension or the space variable on which temperature is varying. Now we can apply FTCS scheme. We have already explained what is FTCS, forward time and central in space. So the forward differencing in time we can see, and then we have taken central difference in space, and all the variables, dependent variables, we can see are written as nth level. Whereas when we have expressed the del u del t, we have written uin plus 1 minus uin by delta t. And here values of temperature, values of u at the entire spatial domain, all the points are known at nth level. We will be determining these values at n plus 1th level. So the obvious outcome of this discretization is ui n plus 1 equal to uin plus alpha delta t divided by delta x square into u I plus 1 minus u twice ui plus ui minus 1, all are at nth level. Very clearly we can see, we can find out ui value at n plus 1th level in terms of all known quantities. Ui at nth level is known, its neighboring value, eastern neighbor at nth level is known, westward neighbor at nth level is known. So all the known quantities, time step is known, delta x is known, so we'll be able to find out ui at n plus 1th level. So this way, if we can sweep from I equal to the first point to the last point, say I equal to 1 to I max, then all the points we can calculate at n plus 1th level explicitly from the values at nth level. So this is called explicit algorithm, and this is very easy to formulate. Only thing is that delta t and delta x we cannot take arbitrarily. They are related and they are to be obeyed. They are to obey the stability requirements. We'll come to that as aspect little later. Now, the right hand side, just recall this discretization. If at the right hand side values are all expressed nth level values, now these are changed to average of n plus 1th level and nth level values. So ui plus 1, this is ui plus 1 at n plus 1th level, ui plus 1 at nth level by 2. So average of n plus 1th level and nth level value by 2. Similarly, ui also expressed that way, and ui minus 1 is also expressed that way, average of n plus 1 and nth level value. If we write it in this way, we are introducing another strategy, and this strategy is called Crank-Nicholson implicit scheme. What we have to do next, the values at n plus 1th level are not known, but now we have these unknown values n plus 1th level at left hand side and right hand side, both the sides. So let us transfer all the values at n plus 1th level to the left hand side, and all the values at nth level on the right hand side. That means the values at nth level are moved to right hand side, and right hand side can be evaluated and it is known, whereas left hand side ui at n plus 1th level is not known, and it is expressed in terms of ui minus 1 at n plus 1th level. This is also not known, and ui plus 1 at n plus 1th level, this is also not known. So the unknown point ui at n plus 1th level is expressed in terms of its eastern neighbor and westward neighbor at n plus 1th time level, which are also not known. R is the quantity alpha delta t by delta x square, it is known. Now if this equation we run from I equal to 2 to I equal to say I max minus 1. Just here itself, if we substitute I equal to 2, we will get in this equation u2 n plus 1. This term, the first term on the left hand side will be u1 n plus 1, and the third term will be u3 n plus 1. So u2, u3, u1, all three quantities are unknown. We will get one algebraic equation in terms of u1, u2, u3 equal to a known quantity. Then we will vary I equal to 3. So then again we will get to another equation. u3 n plus 1 will be the middle term. The first term will be u2 n plus 1, and the third term will be u3 n plus 1. So this is, sorry, I said I equal to 3. So if I say I equal to 3, first term will be 2, third term will be 4. So u2 at n plus 1, u3 at n plus 1, u4 at n plus 1 will appear in the algebraic equation. Right hand side will again be known. So this way, if we keep on varying I, which we have done here, I equal to 2, I equal to 3, I equal to 4. So for each I, we'll get one algebraic equation. And in this algebraic equation, as we have seen, that this coefficient we can write as B, and entire right hand side we can write as C. So we will see for I equal to 2, U2 with the coefficient U3, both are at n plus 1th level, not known, equal to right hand side known C. The first point, which is U1, this is falling on the boundary. So for example, if this is the domain in the figure, if you focus, I equal to 1 to I k plus 1. K plus 1 is the end point, I equal to 1 is the end point, starting point. Now boundary condition means at two extremes I equal to 1 and k equal to 1 are the boundary conditions, and we have given here boundary condition for the dependent variable, that is u, at I equal to 1 we have written the value as a, and I equal to k plus 1 we have written the value as d. So boundary conditions are u equal to a here and u equal to d at k plus 1th point. So in the first equation, the quantity u1 at n plus 1, this was with minus sign, we can look into it, and then this will be minus a, because u at 1 or u1 is known, and that is basically the boundary condition A. So then we can this way substitute I equal to 2, I equal to 3, I equal to 4 and I equal to k, then we will get uk minus 1, again the coefficient uk, and uk plus 1. Now again uk plus 1, this value is basically the boundary condition D, and right hand side is known. So we get algebraic equations for each I value, and this set of algebraic equation, a system of algebraic equation, we can express in this way in matrix form. So this is Ax equal to B, usual matrix equation. A is the matrix which is a known matrix, X is the vector which is unknown vector, equal to the known quantity, known vector. So if we can convert this matrix into a triangular matrix and upper triangular matrix, we will be able to evaluate all these quantities through back substitution. And in this matrix we can see A matrix, the diagonal elements are present, immediate subdiagonal elements are present, immediate superdiagonal elements are present, all other elements are 0. This is called tridiagonal matrix, and inversion of the matrix or converting it into a upper triangular matrix is very simple. We have standard algorithm. We'll learn about that algorithm and we'll apply that. So if we can apply that on this matrix, then we can easily find out all these variables, that means u2, u3, u4 up to uk. u1 at n plus 1th level is known, the boundary condition. uk plus 1 at n plus 1th level is known. That is also the boundary condition shifted to the right hand side. This is a also shifted to the right hand side, and u2 to uk are not known, and this will be now known. So all these values from nth level to n plus 1th level we can proceed. We can find out all these values by solving this matrix equation, and these values will be evaluated in one go. Just after inverting this matrix, we will be able to get u2 to uk as an array immediately. So individually now, what is the value of u2, u3, u4? We need not evaluate. We will come to know all the values just in one go. And this formulation is called implicit formulation. And this is Crank-Nicolson implicit formulation, since the way we wrote the right hand side following the Crank-Nicolson method, we wrote it. So once n plus 1th level, all the values are known, we can go for next step. That means all the values of n plus 2 time level. And this way we can do the time marching from n to whatever level we want to reach. Now, this is a very efficient methodology. We can see very efficient formulation. We can we have no stability restriction. Delta t can be large, and wherever we are trying to get basically the final desired level value quickly, we can go for implicit formulation. Maybe, I'm giving an example that at t equal to 0, we know the basic distribution of temperature, maybe on a plate at different points, and then we want to get it after 10 seconds. So my delta t here can be 5 seconds or straight away 10 seconds. Whereas we will see in explicit formulation, it has to be very small. We have to progressively reach the final desired value. In implicit formulation, in relatively fewer time steps, we can reach the final desired level. So now if we look at two-dimensional heat conduction equation. So the space variable, that means alpha, we have second derivative in x and second derivative in y, in x and y direction, maybe on a plane, and then we are progressing in time direction. Now here also we can write explicit scheme. That means that central differences in the x direction of the variable involving eastern neighbor and western neighbor, uij is the point of interest at nth level, divided by delta x square. Again, uij, its northern neighbor, maybe uij plus 1, and uij minus 1, southern neighbor, divided by delta x square, simple central difference. And here uij at n plus 1th level is not known. We can easily write now uij at n plus 1th level. If we move all other terms on the right hand side, entire right hand side will be known. That will be this bracketed terms into alpha delta t by delta x square multiplied by ui plus 1 uij ui minus 1j, again plus alpha delta t multiplied by uij plus 1 uij minus 1 divided by delta x square. So all the terms are known plus uij at nth level, that will give me as uij at n plus 1th level, and this is again explicit scheme. If we apply Crank-Nicolson scheme here also, what we'll have to do, we have to write the variables on the right hand side in terms of average quantities between n and n plus 1th level, and then we'll apply central difference operator on this variable, which is u at ij at n plus 1th level and nth level by 2. So uij at n plus 1 plus uij at n divided by 2, on this quantity we will apply central difference operator delta x square and delta y square, and this operator means we have clearly written it, you can follow that. So if we do that, we have to further formulate a strategy that we will not go from uij at nth level to uij at n plus 1th level directly. What we will do, we will go from uij at nth level to uij at n plus half level. We'll divide the time step exactly by 2. So if delta t is the time step, first we'll progress delta t by 2, and in this step we'll progress delta t by 2, and uij at n plus half level is unknown, and the central difference operator will apply to the variable at n plus half level in x direction. In y direction we will apply it on nth level. All nth level values are known, but n plus half level values at this stage are not known. So we will be able to write an algebraic equation where n plus half level values are not known, and this will be expressed in terms of right hand side which is known. Having done that, we'll progress from n plus half to n plus 1 level. Then what we'll do, we'll write ij at n plus 1 minus ij at n plus half divided by delta t by 2 equal to alpha. Central difference operator will apply on the variable uij at n plus half level which is known and in x direction, and central difference operator in y direction will apply now at n plus 1 level, and all these values are unknown, and then these unknown at this stage n plus 1 is unknown, so we'll move all the variables at n plus 1 to left hand side, and all the variables at n plus half level on the right hand side. Right hand side is known. Again we'll get explicit equation of uij in terms of uij plus 1, uij minus 1, because we are applying central difference operator in y direction on n plus 1. So at n plus 1th level, uij plus 1, uij minus 1 and uij are not known at n plus 1th level. right hand side everything is known. So again we'll get this algebraic equation, and then we will just be able to evaluate values at n plus 1th level. To explain it little more, the first step what we wrote here, progressing from nth level to n plus half level, that is the first step. So uij n plus half minus uij n divided by delta t by 2 equal to, we can see the right hand side, and the central differencing operator in x direction has been applied to the variables at n plus half level, whereas at nth level central differencing operator in the y direction we have applied. Here these terms are known, n plus half terms are not known, they are moved to left hand side, known terms are moved to right hand side, and then we get this equation, which is b ui minus 1j plus 1 minus twice b uij plus b ui plus 1j, whereas b is given by alpha delta t by twice delta x square. And at n plus half level, these are all unknown. On the right hand side, nth level values are known. We can now rearrange them. Uij at nth level minus a into uij plus 1 minus twice a minus twice uij plus uij minus 1. These are all at nth level and these are known. Now if we vary I from 2 to I max 1 at any given j, for example these are the y direction, this is the x direction. So that means these divisions will be counted by I index, these divisions will be counted by j index, and we are progressing in time direction. So at nth level everywhere value is known, we are calculating at n plus half level. At n plus half level, for j equal to 1, all these values are known because they are boundary values. So this is known. At j equal to 2, then if we vary I equal to 2, if we take I equal to 2, so we will get u at 1j, at 2j, at 3j as an equation. Similarly, I equal to 3, that means u 2j, u 3j, u 4j, and here j is fixed. So you are varying I from 2 to I max minus 1, because why 2 to I max minus 1? When we apply I equal to 2, we get u at 1j, and that is boundary condition. Similarly, when we substitute I equal to I max minus 1, then we'll get one term I max minus 2, another is I max ui max minus 1, and another is ui max. And ui max value is falling on the boundary, that is known. So this way, at j equal to 2, if we apply I equal to 2 to I max minus 1, we will get a tridiagonal matrix, and from that matrix, after the solution is obtained, we will get all these values of I at j equal to 2. Similarly, at j equal to 3, we will get, similarly at j equal to 4, we will get all the I values. So this is called, so in I direction it is implicit. will vary j equal to 1 to 2, 2 to 3, 3 to 4, and for each j we will get a tridiagonal matrix, and through that we'll get values generate values at all the i's. Then we'll complete all the values at n plus 1th level. Having done that, we'll come at nth level. That means second step. And what we will do at the second step? Second step, uij at n plus 1, this is not known, but at n plus half all the values are known. Up to this we have progressed. Now we will progress from here to n. So this is from n plus half to n plus 1. And then what we are doing? We are applying central differencing operator in x on n plus half level, and at n plus 1 level we are applying central difference operator in y direction. Again n plus 1, these values are not known. We move all the variables that are not known to the left hand side and all the variables that are known to the right hand side, and we will be able to follow this equation. A u I j minus 1 plus 1 minus 2a u I j plus a u I j plus 1, all are at n plus 1th level, all are unknown, equal to the values at n plus half level. And a and b, we have written what are the expressions for a and b. And here what we will do, we will take up one I and then we will vary j equal to 2 to j max minus 1. For example, I equal to 1, I am not applying because I equal to 1, all the values are falling on the boundary, they are known. At I equal to 2, then we will vary j equal to 2 to j max minus 1. J equal to 2 means here u1 j minus 1, u2 j, u3 j plus 1. J is fixed now. So basically fixing the I is fixed now, sorry. We are varying j equal to 2 to j max minus 1. Sorry, let me repeat. So I is fixed, I is 2 for example, and then j, when j is 2 here, this is 1, this is 3. Then again j is 3, this is 2, this is 4. So basically fixing I equal to 2, j equal to 1 to j max, from beginning to the end all the values will be expressed in terms of unknown quantities at n plus 1th level, and right hand side is known. So for a fixed I, will vary j 2, 3, 4 up to j max minus 1. So we'll get a tridiagonal matrix, and by inverting that tridiagonal matrix we'll be able to find out all the values at I equal to 2, all j values. So entire this row will be filled up. Similarly, now I equal to 3, we will get all the values. I equal to 4, we will get all the values of j. So at n plus 1th level, then all the values on the domain at all the points will be known. And this time j direction is implicit. We are fixing at I and marching in j direction, implicit direction. So for going from n equal to n plus half, we made I direction implicit, and for going from n plus half to n plus 1, we are making j direction as implicit. That is why it is called alternate direction implicit scheme. And in this alternate direction implicit scheme, we can see order of accuracy in the spatial dimension is second order. And while doing this, we have achieved again second order accuracy in temporal direction. If you look at this discretization, you will be readily appreciating it. Here we have expressed n plus 1th level values simply by Taylor series. N plus 1 ui n plus 1 in Taylor series expansion, the ui n plus half plus del u del t delta t by 2, so on and so forth. Similarly, uij at nth level, again this is backward difference, uij at n plus half minus del u del t by 2 plus 1 by factorial 2 del 2u del t2 del t del x square, so on and so forth. And if we, from these two Taylor series expansion of uij n plus 1 and uij n, if we subtract second from the first, we will get this expression, from where we can write down the del u del t, and we can see if del u del t now we can write as uij n plus 1 minus uij n by delta t. The highest term of the truncated series is a second order term, delta t square. So eventually we have reached second order accuracy of discretization in the time direction. So alternate direction implicit scheme, it is not only second order accurate in space but also second order accurate in time. So we have learned through this explicit formulation, implicit formulation, simple Crank-Nicolson implicit scheme, and alternate direction implicit scheme, which is ADI with higher order accuracy in temporal direction as well. So having done that, since so far we have been mentioning, about the difficulty in explicit formulation, which is basically restriction of grid size in spatial and temporal direction, and this is some form of restriction, otherwise explicit formulation will not work. Whereas in implicit formulation, this restriction in the temporal direction is relaxed. That means in the marching direction is relaxed. So now how can we say whether it is stable or it is unstable? We'll go for that analysis. There are two major sources of errors in the numerical solutions obtained by approximating the partial differential equation. Discretization error, this is the truncation error plus errors obtained by other numerical approximation, obviously numerical scheme. Rounded off error, these are numerical error introduced for a repetitive number of calculations due to round off by the computer. The solution will be stable only if magnitude of error shrinks as the solution progresses in the marching direction, that is from n to n plus 1. The errors should reduce, or in the worst case it should stay at the same level. Otherwise, error will blow up in repetitive calculations. Now what is this round off error? Just, we'll uh, discuss it again. This is a numerical error introduced for repetitive number of calculations in which computer is constantly rounding the number to some decimal points. All of us know that depending on the computer architecture, sometimes it rounds up at 32nd decimal place, sometimes it rounds up at 64th decimal place, but that is called double precision. So even if it rounds up at 64th decimal place, it will introduce some error. Now in repetitive calculations with different quotients, this error will keep on progressing, and this error distribution can be such, variation can be such, that through repetitive calculations these errors will accumulate, and finally this will really distort the solution. So how to handle this situation? Now if A is the analytical solution of the partial differential equation, D is the exact solution of the finite difference equation. That means in the finite difference equation, whatever differencing method we have adopted, for that the solution that was to be obtained, if we get exactly that solution, we'll call it D. But as I said, that a machine, a computer, will not give me exactly D, because if it's a number, a real number, then maybe after 8 decimal place, 10 decimal place, or 32nd decimal place, 64 decimal place, it will be rounded up depending on the computer. And that is what is called numerical error. So if A is the analytical solution and D is the hypothetical or ideal solution of the finite difference equation, A minus D is the truncation error, and also error introduced due to treatment of boundary condition. If boundary condition, if we introduce some approximation or some way, maybe boundary condition can be Neumann condition where derivative has to be defined. Directly value of the dependent variable is not applied. So there we do some approximation. So due to all this, some error can be introduced or may be introduced there. So that is the discretization error, A minus D. Truncation error plus error introduced due to treatment of boundary conditions. And what is round off error? This is N minus D. N is the actual number that machine gives, and D is the number we are supposed to get from our finite difference quotient. And this is valid not only for finite difference, finite volume and finite element also. This is valid in the same way. So this is from the solution of the discretized equation, and this is the number we are getting. So this difference is basically round off error. So N, if that is the solution we are getting from computer, we can say that that is the ideal solution we should get from partial differential equation plus some error. Even though it is very small, it is there, and together we get, when we add it up, we get the number which computer gives to us. Now, as I said, through repetitive calculation, this E may grow. And now we will see how there is a possibility of growth of this epsilon, and how, if it grows at all, then how to reduce that. So this E or epsilon is basically the round off error. Now again, let us go to one-dimensional heat conduction equation and go for FTCS scheme. If we go by FTCS scheme, then we can write UIN plus 1 minus UIN by delta T. Now instead of U, we will write down now the solution which we will get from the computer. If that is N, basically that is the ideal solution plus the error. So di at n plus 1 plus epsilon I at n plus 1, this together is the solution which is we are getting substituting UIN plus 1 minus UIN, so that means minus DIN minus epsilon IN by delta T. Similarly, here on the right hand side, the thermal diffusivity into, we had Ui plus 1 at n minus twice Ui at n plus Ui minus 1 at n. So those are substituted by di plus 1 at n plus epsilon I plus 1 at n minus twice di at n minus twice epsilon I at n plus di minus 1 at n plus epsilon I minus 1 at n and divided by delta x squared. So equation 2 is the equation which is basically prevalent if the solution is valid. Now D is the exact solution of the finite difference equation. So we can straight away write this. That means di at n plus 1 minus di at n divided by delta t equal to alpha into di plus 1 minus twice di plus di minus 1 all at nth level by delta divided by delta x squared. So equation 3 is a valid statement, and equation 2 is also a valid statement. Now if we subtract equation 3 from equation 2, we'll get an expression in error. This is an equation involving all error quantities at n plus 1th level, nth level, at the point of interest, at the eastern point of interest, at the westward point of interest. So this gives basically the distribution of error, and this distribution of error is not known to us. That is why what we will do in x and t domain, this distribution of error we will take as a Fourier series in spatial domain and one exponential in the temporal domain. It is expressed as e to the power at and then a Fourier series e to the power I kmx. I is the unit complex number and k is the wave number. So we will just discuss a little more about the error. Now at ith location, error at n plus 1th level, if that is epsilon I n plus 1, and at nth level if that is epsilon I at nth level, then this ratio, modulus of this ratio, should be less than 1. I explained it earlier that error should reduce in each time step. Maybe at some intermediate time level it may stay at the same level, but never it should exceed, in order the formulation to be stable. For the FTCA scheme, let us examine under what circumstances this holds good. Assume that the distribution of error along the x-axis is given by a Fourier series in x, and the time-wise distribution is exponential in t. I mentioned about it just in the previous slide, while discussing the previous slide. So this error, as I said, this is a Fourier series in x, where k is the wave number, I is the unit complex number, and e to the power at, that is in the it is exponential in t, and wave number k is the wave number. I will just explain it conceptually. Let a wave, all the error propagation are equivalent to wave propagation. Now let a wave travel with a velocity v. The time period, that means the time period of the wave, if it is t, then we can say that time required for the wave to travel a distance one wavelength is t. So wavelength is equal to wave velocity into t. Very simple. And then wave number is nothing but twice pi by lambda, twice pi by wavelength. So this km in the Fourier series is representative of wave number. That means the error propagation, if it is simulated as wave propagation arbitrarily in x direction, then k is the representative wave number. Since the difference is linear, when error is substituted in equation 4 means here, so the behavior of each term in the series, this Fourier series, is same as the series itself. Hence, so instead of taking the full Fourier series, what we will do, we will just take one term. And this is a good representation of the analysis. So this error em x and t is function of x and t is e to the power at. In time direction, it is time growth is exponential into e to the power I kmx. Km is the wave number, and uppercase I is basically the unit complex number. In many textbook, it is written as lowercase I, but lowercase I and j we are writing for each variable. So not to create further confusion, the unit complex number we have used capital I or uppercase I. Now let us, if this is the representative of error term at mth location, e to the power at, e to the power I kmx, then we can substitute equation 4 term by term, and by term by this function em, function of x and t, and then we will get this. You can do it, just practice it yourself. U a t plus delta t e to the power I kmx minus e to the power at e to the power I kmx divided by delta t equal to alpha, and again this is epsilon I plus 1, that means e to the power at e to the power I km x plus delta x. This is twice epsilon xt, so that means e to the power at e to the power I kmx, and this is epsilon I minus 1. So e to the power at e to the power I km x minus delta x by delta x square. So this expression 7, if we divide by e to the power at e to the power kmx, we'll get this e to the power at minus 1 divided by delta t equal to alpha into e to the power I km delta x minus 2 plus e to the power minus I km delta x by x square. Then we can recall this identity that cos km delta x cos theta equal to e to the power theta plus e to the power minus theta by 2. So if we invoke this identity here, we'll be able to write e to the power at equal to this delta t, now go to the right hand side, 1 plus alpha twice delta t by delta x square, and from here it is possible to write cos km delta x minus 1. So again, just look at this term. This cos theta minus 1 can be written as twice sine square theta by 2, and we have done that. E to the power at equal to 1 plus minus 4 alpha delta t by delta x square sine square km delta x by 2. So basically, this is trigonometric identity. Cos theta minus 1 equal to minus twice sine square theta by 2. Now from there we can write epsilon I in plus 1 divided by epsilon I at nth level, and this is the error quantity. Modulus of this should be less than 1. So this is nothing but e to the power at, and modulus of e to the power at is basically, then if we look at here, modulus of e to the power at is basically modulus of 1 minus this, 1 minus this whole quantity. Modulus of e to the power at is modulus of this entire quantity on the right hand side of equation 9, and this should be less than equal to 1. This is the requirement. Now this can be satisfied, and if this is satisfied, then our calculations are stable. Error at no condition will grow, and this part is called amplification factor. It means amplification of error, which is modulus of this quantity minus 4 alpha delta t by delta x square into sine square km delta x by 2. Now this can be this can be done in two different ways. A, we can straight away say if the modulus has to be less than 1, then possibility is there are two possibilities. One is 1 minus 4 alpha delta t by delta x square into sine square km delta x by 2. This quantity is less than equal to 1. And this is very straightforward. In order to obey this, or in order to satisfy this, what has to be done, or what has to be satisfied, is 4 alpha delta t by delta x square into sine square km delta x by 2 must be greater than equal to 0. So we can see that alpha is the diffusivity, it cannot be negative. Alpha t, delta t is the time step, it is also not negative, delta x square. So this quantity is always positive, and this condition always holds good. B is another possibility, because our condition was modulus of this has to be less than 1. So another possibility is 1 minus 4 alpha delta t by delta x square sine square km delta x by 2 is greater than equal to minus 1. Now if that has to be satisfied, we can do simple algebra here. 4 alpha delta t by delta x square sine square km delta x by 2 minus 1, just change the sign, is less than equal to 1. From here, the highest value of sine theta is 1. So we can see that the restrictive condition is alpha delta t by delta x square is less than equal to half. So as I said, that in order this amplification factor, which is modulus of this quantity given by equation 10, we have two possibilities, A and B. Combining these two, we can conclude that alpha delta t by delta x square has to be less than half. So von Neumann stability analysis is this: the error is modeled as a Fourier series and the condition of shrinking error is applied. We obtain a condition for amplification factor. For one-dimensional heat conduction equation, we get this as alpha delta t by delta x square less than equal to half. This von Neumann stability analysis can easily be extended for two-dimensional heat conduction equation. You can do it as an exercise. It is very simple exercise. I will also give indication how to do it in other examples when we will be discussing further. But even now you can do it very easily. If you do it, you will see that the restriction for two-dimensional heat conduction equation will be alpha delta t by delta x square, alpha delta t by delta y square is less than equal to half. So these are the restrictions. As such, I have not mentioned it here. Again, I will do it little later. That alpha delta t by delta x square is called grid Fourier number. So grid Fourier number in x direction and grid Fourier number in y direction together less than equal to half. And you can see if delta x equal to delta y, grid size is same, in 2D it is less than equal to 1/4. However, in 1D, alpha delta t by delta x square is less than equal to half. That we have derived here itself, and all of us know about it, how to go about this problem. So with this, we will finish our lecture today, and we will meet again in the next class for moving forward, taking up issues with more complexity and more involved issues. Thank you very much.